Hello, section 2.4, part 2, continuous random variables. In 2.4 part 1 we did discrete random variables, and we talked about sort of how to think about them. We're going to do continuous random variables now, and I'd like to build on the discrete random variable work because you probably sort of understand that now, and then continuous random variables are a lot easier to understand then. You have this table in your packet, so you should be filling that out. That serves as your notes for this section. All right, so random variable. Remember, for discrete random variables, x takes a countable number of values, like the number of TVs in a household. And continuous random variable, x takes an uncountable number of values, like the weight of a choir member. All right, so you have to, when you can't count things, you have to approach probability in a different way. All right, so now the probability function is going to be totally different. All right, so before we had this PMF, which was just the probability of x, P of x, probability of x. But now we're going to have this thing called f of x, which is called the probability density function. And it's exactly that. It tells you something about the density of probability at a single point. And the way I want you to think of it is I want you to think about a graph where the values of x are on the x-axis, okay, are on the horizontal axis. And then think about, like if this was weight of people, if x was some kind of weight, there'd be certain weights that'd be more common than others, and the value of f of x is going to be higher there. All right, so, you know, there's some curve. All right, and like this, at this point, you know, whatever this value is, that's like the maximum probability kind of stacked up there. All right. And this curve is f of x. The problem is that at any single point, you can't find the probability using that function, all right? Because it's continuous. So for example, well, so we'll talk about that. So like in the very next row of this table, you'll see finding the probability that x equals a. Let's write this down. How do you find the probability that x equals a? How do you find the probability that someone weighs exactly 160 pounds? Well, you don't. That's like impossible, really, for someone to weigh exactly 160 pounds. 0. So the probability of a single point is 0. All right, so we say people can weigh 160 pounds, but the truth is they really can't. There's so many different values, infinitely many values close to 160 pounds, right? And so really probability is considered to be, probability of a single value is considered to be 0. And remember, f of a is not a probability. The amazing thing. All right, continuing. The cumulative distribution function means the same thing it did before. So, whoops, sorry, I'm having a hard time scrolling. All right, so if we want to find the probability, or capital F of k, we're just going to find the probability that x is less than or equal to k. And in this case, what that means is, I'm going to draw that picture again. Here are the different values that we can get, right? That f of x is. And maybe there's some weight. It's like here, and that's k. So the probability of being less than that value ends up being the area under the curve. Oh yes, calculus. All right. So this ends up being whatever the lowest value is. I don't know what the lowest value is. I'm just going to call it negative infinity for now, all the way up to k of that function f of x dx. All right, so you're going to find the area under that curve to find a probability. And capital F, remember, capital F cumulative distribution is a probability. All right, more about probability. So if we wanted to find the probability that x is between a and b, including a or including b, so we do the same thing. So we have that, whatever that curve is, sorry, I drew kind of a different shape that time. All right, but we have some a and some b, and we want the probability of being between them, right? So the probability ends up being the integral from a to b of f of x dx. Similarly, if we want the probability that x is between a and b, but not including a and not including b, we would do the integral from a to b of f of x dx. Oh no, they're the same. But that's because a and b, right, they don't carry any probability weight themselves, right? Remember, somebody can't weigh exactly a pounds, right? So another way to think about that is, I'm going to go back up, hopefully. Let's go back up to this, now that you understand this. Whoa. Sorry if you're getting dizzy. All right. So if we want to just find the probability of a, now that we know we should integrate, this is like the integral from a to a of something. And that would end up being 0, right? Because you take like the antiderivative and you do antiderivative at a minus the antiderivative at a, it'd be the same thing. Or you could think of it as, right, the area under the curve at a single point. So the area of a line is 0, all right? So there's lots of ways to think about that probability being 0. I finally figured out that when I want to scroll around, I should just pause the video, and I did that. Okay, so now how do we find a mean and a variance and standard deviation and things like that? All right, before, and I'm sorry, this formula came out a little weird when I transferred from Google Sheets, Google Docs to Microsoft Word, but if I want to find the mean, the expected value of x, what I'm going to do is I'm going to integrate over the whole range, the whole domain for that function, x, or f of x, and I'm going to take x times f of x. Once again, it's a weighted mean. Instead of x times p of x, it's x times f of x. Notice they look almost the same. Instead of a summation, we have an integral. All right? Instead of p of x, we have f of x. Very, very similar. Instead of over all x, we still have over all x. And I'm just writing negative infinity to infinity to simplify, because we don't really know what the lowest value, this really means the minimum value, and this really means whatever the maximum value is. All right. If we wanted to find the variance, before we saw that the variance was the expected value of x squared minus mu squared. It still is. And now we'll do something similar. We'll find the expected value of x squared, which is going to be x squared times f of x dx, and then integrate that over all possible values of x, and then subtract the mean squared. And then the standard deviation, still just the square root of the variance. All right. We didn't talk about the pth percentile earlier, but now we're going to. If we want to find the pth percentile for a continuous distribution, what I want to know is I want to know what this value is, and we're just calling it x subscript p, so that this value here is p. All right? So, like p%. All right, so if we want that, what we're going to have to do is we want to know what integral, right? What integral gives that? All right, so we want to know the integral from negative infinity, whatever the lowest value is, up to this value of x of p of f of x dx is equal to p, written as a proportion. Instead of you don't write 80, you would write like 0.8, and solve for x sub p. All right, so we want to know what is this value. All right, let's look at an example in our next couple minutes as we only have a little bit of time left. All right, the example we're going to look at is in your textbook, page 114, number 13. Page 1, yeah. They always have engineering examples. So x is the mass of some randomly chosen resistor, and f of x is this function, x minus 80 over 800, and that's for 80 between, or x between 80 and 120, and otherwise it's 0. I graphed this on using GeoGebra, and so this is the value 120 for x, and this is the value 80. And notice this is just a line segment, right, from 80 to 120. And by the way, the maximum value here is 0.06. All right, sorry, I can't really write that. 0.06 is the maximum value of this function. This function has to integrate to 1. So if anytime you integrate, you might add this to your notes, and f of x from negative infinity to infinity, it has to equal 1 because that's 100% of all values, right? So just like if we add up all the p of x values in a discrete distribution, we should get 1, right? 100%. So notice this has to be really short because we're going from 80 to 120. And so that's going to give us the right area, okay? So what we want to know in part A, what proportion of resistors have a resistance less than 90? So somewhere in here is 90, probably about here. And what we want to know is what is this area? By the way, you could use geometry to find that area if you knew this length is 10 and you knew what this height was, right? You could do a 1/2 base times height kind of thing, or you could use calculus, all right? So what we said is, if we say x is less than 90, we said that you just have to find the area under the curve. So our lowest value was 80, and our next, we're integrating to 90 of f of x. So the f of x function is x minus 80 over 800. And you'll have to remember some of your integration rules. All right, so this is like a power rule, x squared over 2 minus 80x. And then you're going to evaluate from 80 to 90. If you do that, I did it, and I ended up getting 5/8 in the end. Yeah. All right. We're supposed to find the mean resistance in part B. So we know that the mean is supposed to be x times f of x dx over all possible values. So my possible values are really from 80 to 120. And now I'm going to do x times x minus 80 over 800. So whatever that ends up equaling. And I did that, and I got 106.67 ohms. A little bit about the mean. A mean's sort of interesting. A mean is supposed to be the balancing point of a distribution. So if 100 is like halfway between these, notice this balancing point's a little bit to the right, 106, which makes sense, right? This side is heavier than this side, right? And so it makes sense that that might be a little bit to the right of 100. All right, that's it.